Hello, everyone. My name is Rachel Minney. I'm a student at West Virginia State University, and today I'm going to talk to you about the research that I've been doing there as an undergrad. So I've been working on synthesizing an aluminum sensing molecule. And this is important because there's a lot of aluminum in Earth's crust. Approximately 8% of it is made of aluminum. It leaches readily as a percolate, and this can be a problem with acid mine drainage. There are a lot of mines in West Virginia and the surrounding states. So we're finding, like this study in Pennsylvania, really high levels of aluminum, more than 1 milligram per liter. Now, the World Health Organization recommends only 0.2 milligrams per liter max should be in drinking water. And this is the same that's recommended by the FDA for bottled drinking water. So having more than 5 times that amount, it can be worrying, especially when you consider the health effects that aluminum can have. It has neurotoxic and neurodegenerative effects. And there's a little bit of public debate on what exact effects it can have on the body. But we do know it can cause diseases like Alzheimer's, it can cause kidney disease, and it can cause bone diseases like osteoporosis. So we definitely want to keep an eye on this and limit how much is in our drinking water. So aluminum ions have unfilled orbitals, and this allows them to complex with molecules. And this is how this molecule, this sensing ligand, is going to work. The oxygens have a lone pair, and they are able to coordinate this to the aluminum, and it forms a dative covalent bond. So when aluminum binds with this molecule, it will luminesce, and fluorescent spectroscopy can be used to determine aluminum concentration in the water. This is going to be very useful for water personnel because they'll be able to quickly and effectively find how much aluminum is in the water. It's going to connect to a DNA backbone at this terminal alkyne site, and that's what's going to allow it to be placed on the sensors and put in the waterways. So there's been work done with this molecule before. Oh, not the exact molecule. The summer of 2018, the amine version was successfully synthesized. Although what happened when they put it in an aquatic environment, they found it was too acidic and it would break down this molecule. So we decided we're going to use an alkene instead. And this is where I come in. I get to synthesize this molecule. I started work on it in summer of 2019. I have successfully completed only 2 of the steps so far, but I want to point out that this, we had a previous synthesis that we started, and ultimately we decided that it would be better to go to this synthesis for a few reasons, and I'll show you why. First, here, you would have to use a protecting group on the alkyne. You're going to perform a Wittig reaction, which is going to join the 2 molecules to give you your final product. And of course, you'd have to have a deprotection, both here for this molecule's protecting group, and here, and here. So you're looking at possibly 3 different protections. Whereas with this reaction pathway, you only have to do a protection here, and you can use this same one on this molecule. That way, when you get over here to this step, you only have to do 1 deprotection step. So that's going to save, it's going to save a lot of time, it's going to save a lot of materials. So ultimately, this synthesis is better than the previous. This one was done in summer of 2019. This one has been executed since fall 2020. So I'm going to go through the steps individually and just tell you a little bit about what chemicals I'm using and what the yields look like. So for the first molecule, this one, the only thing that really needed done with it before reacting it was to put a protecting group on the alcohol. There are a few protecting groups that were used just to see if they would work, but the pivalate group is the one that we're ultimately going to use because then we can use the same thing on the second molecule, and like I said, only have to have one deprotection step. This is just another protecting group that could be used as the methoxy protecting group. And this is a methoxy. And as you can see, 28% yield, 20% yield, and 39% yield. So this was the best yield. These yields do still need to be improved, but that is future work. So here's the synthesis again. Now we're going to talk about this pathway. So the first thing that needs to be done here, this alcohol needs to be protected. And like I said, we're going to use the PIV group. It gives us only one deprotection that we'll have to do. The second thing that we need to do, we need to turn this aldehyde into a terminal alkyne. And a good reaction to use for this is the O'Hara-Bestman modification of the Sievert-Gilbert homologation. It has several steps, as you can see, and the first two steps had a much better yield individually. The third step is abromination. Now, this bromination on this specific molecule has not yet been attempted. What's happening at the moment, I'm working to do abromination of toluene just to see if the conditions that I'm using are going to work with this molecule. The step after that, it's going to be an Arbuzov reaction. This uses triethyl phosphate here. And this is an alternative to the Wittig reaction that was originally going to be used in summer of 2019. The reason that we want to do this one over the Wittig, we don't have to put a protecting group on that terminal alkyne. So once we get the triethyl phosphate put on there, we can join this molecule with the one that we previously made, that we put the protecting group on. And we can do this just using potassium tert butoxide and THF. So under these conditions at room temperature, given just a few hours, we should be able to join these molecules. And then that only leaves one step, which is the deprotection. And since we went through and redesigned this synthesis, we only have to do one deprotection now. And after that, we should have our target molecule. I want to point out this deprotection can be done in a few different ways. Using sodium hydroxide, ethanol, and water, that's just one possible way. This actually can be done using tert butoxide. So it's possible in this step that the protecting groups will come off, and that would be great. All right, here I just wanted to include a picture from the lab. This is a reflux condenser that was set up for the bromination of toluene that I was talking about. Just a little reaction, because everything right now is really, we're still like in the trial stage. I haven't tried to upscale these reactions too much. I'm still working to get the yields up in general. So my acknowledgements. I would like to thank West Virginia State University, West Virginia Science and Research Higher Education Policy Commission, NSF EPSCoR, and NASA. They've all made this research possible by their funding and support. The ligand was designed by Dr. Michael Norton at Marshall University, and the synthesis of this ligand has been supervised and directed by Dr. Michael Fultz at West Virginia State University. So here's the overall synthesis again. I will be on here Friday, March 5th from 2 to 4:30 p.m. to answer any questions live that you may have, so go ahead and post them in the comments. Otherwise, if you have any questions, post them, and I will try to answer them for you. I will be checking on this and keeping up with this at least through March 11th. So if you have any questions or comments, feel free to share. And thank you for watching.